All right, well, welcome back. I apologize if the audio of this is really, really bad, but I don't have a nice wireless mic in order to do this. I'm doing it from Smartboard and all this other cool stuff, but you don't really care about, because all you care about is how do you solve a rectangular page design problem where you're given 64 square inches of print and you're given margins. This is a very popular problem that you would see in a calculus textbook, in optimization areas, and also in pre-calculus when you're dealing with rational functions. Now, the question that we're trying to do is we want to solve this. What should the dimensions of the page be so that the least amount of paper is used? All right, the least amount of paper is used. Now, in order to figure this one out, we have to come up with this equation. Now, sometimes books give you the equation, other times they do not. Well, I'm going to show you how this equation comes about, and then we're going to use it to solve this. And we'll need our calculators. If you're in calculus class, you have to use derivatives and critical points, but right now this is for, we're just going to deal with pre-calculus and calculus. Without further ado, when you're deciding this, what we have is a rectangular page. So a rectangular page means a rectangle. And where you have 64 square inches of print inside here. Now, there's a bunch of different ways, all right, to solve this. But we do know that the margins on top of the page are each 1 inch. 1 inch, all right? And we know that the margins on each side are 1.5 inches. 1.5 inches, 1.5 inches right here. Okay. So, now we got to figure out how do you figure out the volume, or actually maximum area of this rectangular piece, which is located right here. Now, to do this, we're going to give our values some dimensions. We're going to use x and y. Now, you can use x and y. X and y can be either inside, all right, of that one sheet, or you can put them outside. I'm going to put them on the outside because most pre-calculus books have them on the outside. However, it's actually a lot easier to create an equation for calculus if you actually put these dimensions on the inside. But for all intents and purposes, I'm going to show you how you can get this equation right here. So, without further ado, this is what we know. All right, we know that our area of this page is going to equal x times y, right? Because that's length times width, and that's how we find area of a rectangle. Now, we need to put this in terms of two variables, all right, x and y. Now, you could pick two different variables if you want to. I'm just using x and y because they're very popular, all right? Now, the next thing is I want to put this in terms of one variable. And I'm going to say I want to put this in terms of x, y, because I have x up here, and that's what I'm going to say to do. Now, to do this, we're going to have our other area. Well, our area of this inside portion is going to be 64 inches. Well, 64 inches is actually going to be, all right, length times width again. However, this length is going to be x, all right, minus 3. And then you're going to have the top, which is going to be times, all right, so this is x minus 3. How did you get that? We took our x, and we have to subtract these two margins, which is 1/2, or 1.5 and 1.5, which is 3. We're then going to take our y value, and we're going to find out what this value is by taking y, and we're going to subtract these margins, which are each 1 each, so it'd be 2. From here, I'm going to solve for y. I'm going to solve for y because I'm going to use that to substitute it in for this y value here. So solve for y. So right here, we're going to have 64. We're going to divide by x minus 3. And that's going to equal x, so y minus 2. We're going to add, move this over a little bit. All right, we're going to add 2 to both sides. We have 64 over x minus 3. And add the 2, and that equals y. We're now going to take this and we're going to simplify it. All right, a little farther. And I'm going to get a common denominator, so I'm going to take 2 times x minus 3. All right, and multiply that by 1. That's going to be plus 64 over x minus 3. Simplify this a little farther. We have 64 plus 2x minus 6. I distribute that through. And then we divide that all by x minus 3. And that is going to equal y. Answer. Now, when we simplify this, we'll have 58. All right, 64 minus 6 is 58. Plus 2x. And again, that's not very clear. All right. 58. All right. Plus 2x all over x plus minus 3. So now that's our y value. We're going to take that and substitute that into here. And so when we do so, you see that, all right, we're just going to equal all right, x, which is the same. We have 2x, my change around, plus 58, all right? You can see that right there. Yep, x plus 58 all over x minus 3 because we're multiplying those two together. And that's how we get this area formula. Now, from this area formula, we want to figure out where is the least amount of paper being used. So least means we are looking for a minimum value. So this is where you want to take out your calculators, all right? So if you take out your calculator, all right, and you take this over here, and we're going to go to our y equals, all right, I'm going to clear all my stuff that I have on here already, so any stuff you have, clear that out. I'm going to punch this in now. We're going to punch this in going, all right, the quantity, x times 2x plus 58, close parentheses. So you see that? All right, and then we're going to divide that by the quantity x minus 3. Make sure you use parentheses correctly, or else you're going to be dividing a bunch of things that you don't want to do. From here, we're going to graph this. Okay, so I'm going to go to Zoom 6. All right, that's a standard window. You may or may not see this right here. All right, and there's our first graph. And then we see nothing on the other side. So we're missing something. Well, if we think about this, we can kind of think about the graph. And what we have here is, from here, we actually have a vertical asymptote, right? Vertical asymptotes are found when the denominator equals 0. They're undefined values, but there's not a whole. So we have to have a vertical asymptote of x equaling 3. Now, on this calculator, we can see that we do not have a value at x equaling 3, all right? And actually, when you see this, all right, you don't see anything at all. And so what we're going to do is we're going to change our window. We're going to change our window, and we're going to make this, all right, a little bit bigger. Okay, and let's just say we go to 20, because I'm not really sure exactly where it is. We'll go over here. We'll go a scale of 5, just nicer. We'll go exponent. We don't have any negatives, but I'll make this, and let's just make this 150. We'll see how this goes. All right, 150, and we'll go by scales of 10. All right, for our y's. Graph that. All right, there is our first one. There we go. Please work, please work. Oh, we see it right here. Okay. Notice how we have this. All right. We're going to now have this on here. Okay. So now when you look at this graph, notice how we have our vertical asymptote. Our vertical asymptote, once again, is going to be at 3. Now I made this as a scale of 5, so this is actually a 5 or 10. All right. Go back to here. That's my window again. Window was scale of 10s, so you can't see this, but really our vertical asymptote right here is going to be at, all right, x equaling 3. And we know that by looking at our equation. And really our minimum is located right there. So we are going to find our minimum by going over here now. And what we're going to do is we're going to take this and we're going to go to second calculate, or second trace, and we're going to minimum, that's 3. And so we have this, and we're going to go over here. And we're going to keep on moving our cursor until we get to a point that's going to be right where our minimum is. And you can see where minimums occur when it's going from decreasing to increasing. All right, decreasing to increasing. So, come on. And I'm going to press enter right there. And I'll go over here. All right, tap it a couple times. My computer is really slow. Probably a lot faster for you. All right, come on, keep on going. Come on. You can do it. Come on. All right, almost there. A little bit farther, a little bit farther. All right, keep on going. I'm sorry, it's taking forever. All right, and stop, please. Stop right there. And there's the left side, or the right side of that min. I'll press enter again. It's just guessing it, and we have this. All right, so we found out that our minimum is going to be located, all right, this is going to be located right here at when x equals, all right, when x equals 12.79796. So what should we do, or what should the dimensions be? So that's my x value. This y value that we found, remember the y value, actually this is our area. So this is not the y value. So in order to figure this y value out, what we're going to do is we're actually going to plug this back into one of our equations. And right here, we're just going to plug it into this equation, right, where we solve for y. And y is going to equal this one right here. So we're going to plug in, okay, that 12 we have, all right, so we're going to take, I guess, look at this again. All right, we'll have our 2x, and our x is going to be 12.798 around 3 decimal places. All right, and that's going to be plus 58. We're going to divide that by x, so it'll be 12.798. All right, and that's going to be minus 3. And I believe that is correct, and that's our y value. All right, that's our y value. With our calculator, figure out what our dimension is. So that is our dimension. So our x value for our length or width, our y value is this, and that's how we can figure out our answer. Now, what is the domain of this function? So you probably want to figure this out, find that value. All right, I'll just leave it there just to save some time. But the second part, I added an extension of this problem, is what's the domain of this function? Under the constraints of this problem, well, the domain of this function, if you look at this, well, if you think about it, we have a vertical asymptote right here, which we know is at x equaling 3. Now, some people could say this domain is all real numbers, okay? It could be all real numbers except x can't equal -3. That's normally how we find the domain of a rational function. All right? However, in this one, we notice that, all right, there appears to be, all right, negative values for x, which we can't use. And over here, when we get over from 0 to 3, all right, this 3 right here, we notice that all of our areas are negative. Well, we can't have negative areas there either. So actually, the domain of this function is wherever the area, because remember that's what we're finding, wherever the area is positive. So where is our area going to be positive, all right, greater than 0? Well, look at this. We see that it's 0 or greater than 0 for all x values, which are going to be greater than 3. Greater than the vertical asymptote. So our domain with the constraints of this problem are actually all x values greater than 3. Okay? And where do we get this 3 value from? Basically, that's where the vertical asymptote is. Okay? And we have to go to the right of that because that actually gives us values we can use. Okay? So, with that, all right, we found an equation. We found the values of this equation, dimensions, by using the equation that they gave us, going through and finding that on the calculator, changing our window, all right, finding what our x value is, finding them, plugging that in to find the y. We then found where the domain would be, where it will be all x values greater than 3. And this is how you would solve a rectangular page with the image in the middle. Very popular, both again with projectors and calculators. So hopefully this helps out. Hopefully this is a good explanation for you. And good luck and God bless in the rest of your problems. I'm going to check out some other videos that I have coming up soon.